Hey everyone. In this last video, I'm going to talk briefly about residuals for discrete data regression. Okay, and as we will see, once we kind of talk about models with discrete outcomes, the basic residual plot that we used in the linear regression framework is not as informative. So we need to kind of find an alternative in order to evaluate violations of our basic, assumptions and identify outliers and so on. Okay, but before we get to the actual residual plot, let's briefly talk about error rates and comparisons to different types of or comparisons between models in order to evaluate the model fit of a specific logistic regression. Okay. Again, we're working with one of the logistic regressions that we estimated in one of the previous videos. We're predicting presidential vote choice in favor of the Republican candidate in the 2000 US presidential election based on ideological self-placement and education, as well as the interaction between those two predictors. Okay. Now, based on the model, we talked about different types of predictions that we can make based on the model and based on the predictors. And if we want to evaluate the fit of a specific model or between two different model specifications, the first thing we can do basically to evaluate within sample fit is to just compute the predicted probabilities for each individual observation in our data. We can do this using the fitted command, which is basically equivalent to the predict command that I showed you in one of the previous video with the additional option or the additional argument type equals response. So this is gives you the predicted probabilities based on the model for each of the individual observations that are included in the sample that we use to estimate our to estimate our logistic regression. Okay. Then we can basically do two different things. We can compute the error rate of that specific model. Okay, and we can use that to compare it to a different, to a different model specification. But we can also compare it to what is called the null model. The idea behind the null model is basically suppose that you didn't have a logistic regression, you didn't estimate any model. Okay, what is the best prediction that you can make for this dichotomous outcome that you have? Okay. Basically, what is the naive prediction without running any regression, and how good is your performance based on that naive model? Okay, and it turns out if you have a dichotomous outcome measure where you have basically a proportion of zeros and a proportion of ones, the best prediction that you can make based on or without estimating any model is to predict the modal category for each of those observations, right? So you have a set of 1,000 observations. You know that of those 1,000 observations, maybe 60% are ones and 40% are zeros. The most naive basic guess would be then to basically predict a 1 for each observation, because the probability of observing a 1 is 0.6. And based on this very naive null model, you would have an error rate of 0.4, of 40%, right? If I predict a 1 for each individual observation, and there are 60% ones, then I'm right 60% of the time, and I'm wrong 40% of the time, right? So this is basically the baseline that we will compare our logistic regression model fit to, right? Because we're not starting with like 0% correct predictions, or 50% correct predictions. We're starting with basically the number of correct predictions if we just assign the modal category to each individual observation. Okay. In our case here, where we're predicting Republican vote share, this error rate is 0.46, right? So that means the modal category is basically across all observations, 54% vote for the Republican candidate. If we then assign that vote for each individual observation, we get back a error rate of 0.46. Okay, so now how well does our logit model compare to that? In order to kind of compute the same error rate for the logit model, what we can do is we can basically take our predictions that we just computed up here for our 1,200 observations. And for each of those observations where this predicted probability is larger than 0.5, we basically assign a 1. And for each observation where this predicted probability is smaller than 0.5, we assign a 0. And then we're comparing this to the actual observed y, which is either 0 or 1. And if both are consistent, then we have a correct prediction. And if they're inconsistent, then we have an incorrect prediction. Okay, and we can directly compute the error rate by basically computing the average of this logical statement, which again is 0 if we don't have a consistent prediction and observation, and 1 if we have a consistent prediction, or if we have a prediction that is consistent with our actual observed value, right? And we see here now that our error rate is 0.23, right? So 23% error using this logit model. So this is obviously quite the substantial improvement compared to this null model, right? We could now, proceed and compute these error rates with different types of models and basically proceed with our model selection based on that, right? Keep in mind, however, these error rates, of course, provide some initial indication of model fit, but they're not perfect. They have a couple of problems. For example, they don't necessarily distinguish between, small, very small probabilities, or if we have very rare events or very frequent events, then these kind of model fits based on simple error rates that are based on assignment of 0.5 can actually be problematic and not really tell us whether a model is better, even though it actually performs quite well. Okay, so the error rate can be useful as a summary, but it's ultimately, it doesn't tell us the whole story. Okay, kind of moving on beyond kind of simple error rates, we can also directly look at residual plots for discrete data regression to evaluate how well one model fits our data, or a comparison of two different models fit our data, similar to how we did it in the linear regression framework, right? So we can define residuals for logistic regression the same way we did it with linear regression, as basically the difference between our observed value and our expected value. The expected value, of course, is the predicted probability based on our logit model up here on the right. Okay. We can directly compute these residuals by both computing the predicted probabilities as well as our residuals, and then plotting them, where on the x-axis we will plot the predicted probability to vote for the Republican candidate, and on the y-axis we will plot the residual, so the deviation between the observed value and our predicted probability, right? As we can see, the plot looks very different from the residual plots that we saw in the linear regression framework. The underlying problem is that it's not only the case that our outcome measure is dichotomous. Essentially, due to the fact that the outcomes are dichotomous, either 0 or 1, the residuals themselves are discrete as well, right? They're either basically y, or for y equals 1 minus the expectation, or minus the probability of observing a success, or 0 minus the predicted probability of observing a success, depending on whether it's a 1 or a 0 in the actual outcome measure, right? So obviously this type of residual plot is not really helpful for us to evaluate issues with model fit, potential outliers, deviations from like linearity and these assumptions, right? So one alternative that is discussed in the textbook is to use a binned residual plot, okay? And the idea behind this binned residual plot is that we essentially, rather than looking at individual residuals for individual observations, we basically divide the data into different bins, different categories of equal size. So we have equal numbers of observations in each bin. And then we plot the average predicted probability as well as the average residuals for that binned observation. And that gives us a plot that is, again, very similar to the original residual plot that we had in the linear regression example. And it allows us to basically evaluate deviations from our assumptions, or compare the fit of different competing models. Okay. Of course, the challenge from a computational perspective is to kind of divide up these observations into equally sized bins, and then basically compute the average residuals and the average predicted probabilities. We also need a kind of additional guidelines to evaluate whether deviations are actually kind of outside of the range of residuals that we should observe. In order to do that, we can basically compute the 95% confidence intervals for the binned residuals to kind of give an indication of where, if our model is true and if all of our assumptions hold, where should those residuals fall. Okay, and our plot here includes this kind of helpline for the 95% confidence interval. If we look at the result here, we now see, of course, a smaller number of points, because each point represents now a bin that includes a certain number of observations. In our case here, we set the group size, the number of groups, to 15. So we have 15 points here with a size of around 80 or 60 observations within each bin. And we compute the average predicted probability to vote for the Republican candidate and the average residual across all those observations. Okay, and these gray lines represent this 95% confidence interval that indicate basically the range in which 95% of those binned residuals should fall if the model were true. Okay, and we see that based on these binned residuals, this model appears to fit the data fairly well. We don't see problematic outliers, or, for example, nonlinearity or other related issues that we discussed in the past. Okay, we'll again go through the code for these binned residual plots in another applied example in the Q&A session, but make sure to kind of go through the code here, maybe run a different model and try to create a different binned residual plot as you kind of go through the lecture code. Keep in mind that one of the things that we have to do with this binned residual plots is we have to make a decision as to how many bins we should look into. And there's a trade-off between basically having enough resolution between our different points. So we don't want to have too few points in order to kind of look at local non-linearities and things like that. But at the same time, we need enough observations in each bin, so in order to not have too much kind of noise between each of these bins, right? So in the examples that I show you and that are also discussed in the textbook, the bin size is around, between like 60 and 80 or something like that. So between 60 and 80 observations in each individual bin. But depending on your specific substantive example, you might go with a slightly higher, slightly lower bin size depending on your actual data. So whenever you create these binned residual plots, you have to play around with the bin size itself and make sure to have enough resolution to really kind of evaluate whether there are non-linearities or things like that, but at the same time have sufficiently sized bins themselves. Okay. All right, this concludes our kind of week on working with logistic regression models. I showed you a lot of coding examples, so I know this was a lot of material, but I think this will be a useful resource going forward as we work with not only logistic regression, because a lot of these techniques also apply for generalized linear models as well. So with that, I'm going to leave it at that for now, and I'm looking forward to our next Q&A session on Monday, where we'll go through some of those coding examples with a different practical application as well. So I'll talk to you then.